So galaxies in intergalactic medium have a sort of ecological interplay. The gas comes into galaxies, gets expelled from the galaxies. This is where metallic line absorbers have to come from. And I already mentioned that very high column density ones probably are associated with galactic disks or progenitors thereof. As the line of sight towards some high redshift quasar goes through space, it can encounter more than one of these. And here is a good example of a quasar, and along the line of sight to this quasar there is a whole number of separate metallic line absorbers, each of which we believe now is affiliated with some sort of halo of some small galaxy or another. And the way to find out is to first take deep images of fields around those background quasars, identify galaxies around them, get the redshifts, and see if any of those actually correspond in redshift to one of the absorption line systems. This was now done for a large number of these, and in fact, essentially every time there is an association of a galaxy with a given metallic line absorber. Even so, some of those absorbers can be a very large apparent radius from the galaxy. And we know that this is the case because we can absorb multiple ionic species, not just one absorption line, but a whole number of them, which then correspond to the same redshift, and they're matched against the galaxy's own redshift. So here is an example of a whole number of those in one of the deep fields. And those galaxies tend to have pretty much properties of field galaxies at the same redshift, which is reassuring. Now, what about damped Lyman alpha systems, which we always thought were counterparts of high redshift disks? For some number of them, we can also detect Lyman alpha in emission that's offset from the absorption line of sight. And so here is an example of a quasar with a damped Lyman alpha object present. Then in a plot on the right, you can see a spectrum from blue to red, and the orthogonal direction is along the slit. There is a gap that corresponds to the damped absorber, and just offset from it is a blob that corresponds to emission from the same absorber. From the strengths of those emission lines, from their separation from other properties, it was concluded that indeed they're perfectly consistent with being disks or young disks or progenitors of young disks at high redshifts. So if metallic line absorbers associated with galaxies, they should also cluster like galaxies. And in fact, they do. Here is a comparison of essentially two-point correlation function for the metallic line absorbers, just in radial coordinate, because that's the only one we can measure, and also for Lyman alpha clouds. Lyman alpha clouds are also correlated, but much, much less. So metallic absorbers do correspond to high redshift galaxies, whereas Lyman alpha clouds are still material that's in a linear regime that belongs to large-scale structure, not to galaxies themselves. And then we can compare how the absorbers of different types evolve in redshift. As we look at hydrogen absorbers, their numbers increase with redshift, as we already noted before. For the metallic line absorbers, we see first looking from high redshift towards us, meaning in the direction of time, we see an increase as you build up galaxies and star formation, presumably, and then things roll over or flatten out. So this is exactly what we would expect from this picture, in which galaxies are built up slowly, then they eject gas out, and so the metal-rich intergalactic medium is also being accumulated in time. So I mentioned that damped Lyman alpha absorbers are likely to be progenitors of present-day disks. And one way to look at this is to look at their chemical abundances. The column density is so high that in addition to hydrogen, we can measure various metallic species, and from that we can infer metallicity just as we would for stars. Here are the histograms comparing metallicity distributions in damped Lyman alpha absorbers, the solid blue, with metallicities of stars in the thick disk of the Milky Way on the left, the red one, and the thin disk of the Milky Way, the green one, on the right. As you can see, they overlap, but Lyman alpha absorbers are much closer in their metallicity to the thick disk stars, the old disk population, than to the thin disk stars, which are just relatively recently made, chemically evolved systems. And just as we looked at the history of chemical enrichment in galaxies, we can do the same thing now for absorption clouds. And here is the plot of the metal abundance of damped Lyman alpha systems as a function of redshift. The individual red dots are individual objects, and then their bin, and those are the big error bar crosses. So you can see there is a gradual increase. You start with a broad distribution tending to be low metallicity at high redshift, and you gradually climb towards almost solar abundance at low redshifts. Now, one has to be aware that different types of absorbers may be evolving in a different fashion. In fact, they correspond to different parts of galaxies. So damped Lyman alpha absorbers are kiloparsec scales, disk scales, whereas Lyman alpha forest clouds may be at hundreds of kiloparsec scales. On the other hand, you can look at things like quasars, whose metallicity we can also measure from their spectra, and they can be up to 10 times solar. They probably correspond to regions in the very cores of their host galaxies or near the black hole. So the chemical evolution will proceed at different pace in different environments. It will occur faster in the densest environments where you get more of recycling of stars and so on. But we can now probe that over both range of scales. So we can add up all this hydrogen that is then to be used for star formation in galaxies. And if we have proper census of absorbers per unit redshift and so on, we can integrate that, as briefly shown here. So from that, we can then deduce the evolution of the, say, omega in hydrogen gas that belongs to these clouds as a function of redshift. And so here it is, compared to the measurement of the local stellar density, that's the red point in the left, upper left, as well as some of the theoretical models. And you can see that there is approximately 1 part in 1,000 of omega in hydrogen gas that belongs to these clouds. You may remember that omega baryons, all baryons, is approximately 0.045, which is so 45 times this. But the omega of stars that we see in galaxies is only something like 5 times 10 to the minus 3. So this is a fraction, but sizable fraction, of all material that we see in stars. So to recap, the intergalactic medium is forming cosmic web. It's associated with large-scale structure that's still collapsing in a linear regime. But metal-rich parts in the highest column density hydrogen clouds are associated with galaxies, pieces that have already fallen together and made stars. The intergalactic medium is almost entirely ionized from here out to redshifts about 6, at which point you start to get more neutral hydrogen because stars and quasars simply didn't have time yet to reionize it fully before then. The metals themselves come from galactic winds, products of stellar evolution that have been expelled from galaxies and mixed in with the rest of the intergalactic medium. And these studies, using absorption systems, using quasars or gamma ray bursts as background lights, complement other ways of studying galaxy evolution. In the next chapter, we'll finally look at galaxy formation itself and cosmic reionization in more detail.